Okay, the most interesting for us compound is the parent compound from 1 to 2 most iron-based superconductor family. It's europium iron 2 arsenic 2, because here we have, in this compound, we have two most-Bohr elements, europium and iron. In this compound we have two magnetic sublattice too. The first is connected with iron 2 plus 3d itinerant electron, is the spin density wave magnetic order type, and magnetic order temperature is about 190 K. The second is connected with europium 2 plus for a localized electron. It is A-type antiferromagnet with nil temperature being about 90 K. A type antiferromagnet of europium 2 plus is moment means that I coupled ferromagnet is within the plane, but antiferromagnetic between the planes. The next slide shows us the phase diagram, effect of pressure versus for this compound versus pressure, and what we can see that with increasing pressure, spin density wave order temperature increase and disappear in this moment, and between 2.5 and 3 gigapascal superconductivity appears. What is important, and what we can see here, the valence of the europium change with increasing pressure from 2 plus to 3 plus. Superconductivity can appear also by the doping. We can three possibility doping. The first is the Hall doping, when we substitution of potassium for europium, or electron doping, when we substitution cobalt for iron, and isovalent substitution, when we substitution phosphor for arsenium. Here we can see the optimal substitution level and the higher superconducting temperature for each of these group. The next slide shows us the effect of dilution of europium sublattice with non-magnetic ions, and we can see that spin density wave order disappear with substitution level when increase, and the most effective element is a barium, because when we have a 50% of barium we didn't observe any spin density wave order, but okay, now we can go to our compounds, our measurements. The first part of my results is connected with 5 sample. Here we have a relative resistivity for this 5 sample for three parent compounds and 2 superconductors. This resistivity is of course relative to resistivity in room temperature. Here we see a characteristic anomaly characteristic for magnetic order appearance, and here we have the first superconductor. We observe a very interesting behavior in 20K, because we see transition to superconducting states, but in the 10 Kelvin we see that resistivity come back. And here we have the second superconductor. We observe the characteristic transition to a superconducting state, but not to 0. Most-Bohr spectroscopy is our main method. What we can do, the little basic information. We use the source. We have a source emitting a very narrow single gamma ray, and we absorb this and detect passing photons. When we have a resonance, the count goes down and come back. This is of course versus velocity, versus Doppler velocity, because we modulated energy using by Doppler effect. The source for iron 57 is cobalt 57. Here we see the decay. We use this line with energy 14 0.41 keV. What we can measure? We can measure the hyperfine interaction. Which hyperfine interaction? The first hyperfine interaction, what we can see isomer shift. Isomer shift is connected with when we have interaction electron density with charged nucleus. We observe that ground states of iron nucleus change and excited state change too, but the shift of excited states is bigger, and it gives us information about density of electrons in the nucleus. The second is electric quadrupole interaction, is described by quadrupole splitting in Mossbauer spectroscopy, and it gives us information about electric field gradient. Here we have a simulation when quadrupole splitting is bigger and smaller. And the last one is magnetic dipole interaction. In Mossbauer spectroscopy is described by magnetic splitting, and it gives us information about magnetic hyperfine field. And here we have a simulation for the higher and lower magnetic hyperfine field. Okay, so now I can go to our results. It's iron 57 Mossbauer spectra for parent compound. We see that in 300 kelvins all spectra is paramagnetic, but upon with decreasing temperature we observe some changes due to appears magnetic order with spin density wave type. The temperature of spin density wave is practically the same for these two compounds. The amplitude is practically the same for these two compounds too, but the spectra looks a little different, and this spectra is something between this and this. It's connected with the shape of spin density wave. And now iron 57 Mossbauer spectra of europium, iron 2, arsenic 2, but for our superconductor, we can see that in 300 Kelvin we have a paramagnetic spectra, but in lowest temperature we observe some magnetic species. And what is important, in nearest temperature, the near temperature of europium ordering, we observe some transfer field from ordering from magnetic ordering europium to iron nuclei, and it is about 1 Tesla. Okay, before I show you europium 151 Mossbauer spectroscopy results, I can tell you some basic information about this spectroscopy. We use as a source we use the SAMR 151, and we use this line with energy 21.6 keV. Here we have a shift scale of europium 151 in Mossbauer effect, and we can see that europium 2 plus is here, and the shift of europium 2 plus is about 1, but europium 3 plus is here, and isomer shift for this element is about -10, so we can easily distinguish europium 2 plus and europium 3 plus in our compound. When we have a quadrupole interaction, we have a 8 line, but when we have a magnetic hyperfine interaction, we have 80 lines in Mossbauer spectroscopy. But we don't see every lines due to the half width of this line, and here we have a simulated spectra for magnetic hyperfine field being 27 Tesla and electric field gradient being 0. Mossbauer spectroscopy is really sensitive to angle between the main axis of electric field gradient and magnetic moment. What we can see on this simulation. This is a simulation when this angle is being 90 degrees, and so the momentum is in the AB plane, and here we see the simulation when this angle is 0, so this moment is along the main axis of electric field gradient. And Now we can go to europium 151 Mossbauer spectra for form compound, two parent compound, and two superconductors. What we can see especially interesting, it's in our superconductors we observe the small contribution due to the europium 2+. Here we have a 7% and here we have a 8% of europium 3+. And the most interesting results is in the low temperature. Here we see that these spectra look a little different, especially in this line. It is connected with reorientation of magnetic moment on europium. So here we can distinguish, of course, this angle. So in parent compound we observe that this angle is 19, but for this superconductor is 44, and for this superconductor is 30. Mossbauer spectroscopy is not sensitive to type of this reorientation. So here we can see reference to the neutron diffraction measurement, how this canting antiferromagnet looks like. Okay, now I can summing up the first part of my results. Spin density wave fades with increasing doping level, weak magnetic orders survive across the region of superconductivity, europium 2+ order magnetically regardless of cobalt and calcium substitution, and europium moment rotate from the A-axis in direction of the C-axis. 4F magnetic order and 3D superconductivity coexist in the same volume. And now we can go to the second part of our results. It's connected with europium iron to arsenic 2 with nickel substitution. Here we have a phase diagram for this compound. We see that with increasing nickel content, spin density wave order change, it's decreasing. And what is important, the temperature of europium 2+ magnetic order doesn't change, but type of this order change. Here we have we measurement this six sample, and here we see relative resistivity for this sample versus temperature, of course relative to resistivity in room temperature. For this 5 sample, when X is lower than 0.12, we observe the characteristic anomaly connected with spin density wave order appearance, but we don't we didn't observe this for these two compounds. We didn't observe any superconductivity down to 1.8 Kelvin. Okay, so now the iron 57 Mossbauer spectra for 6 compound in 4 temperature, 300 Kelvin, 80 Kelvin, and 2 lower temperature, just above magnetic ordering of europium and below this temperature. What we can see that in 300 Kelvin every spectra is paramagnetic, but upon cooling we observe some magnetic suspicious, especially for this 5 compound. Here we have a 100% of magnetic suspicious, but here we see 2 suspicious, one non-magnetic and magnetic. Contribution due to the non-magnetic suspicious is decreasing with decreasing temperature. What is important for this 4 compound, we see that the spectra below and above temperature of near temperature europium is a little different. It's connected with transferred magnetic field from europium to iron nuclei, and here we can distinguish the angle between this transfer field and main axis of electric field gradient, and it's being about 40 degrees, and this magnetic transfer field is about 1.4 Tesla. Okay, so in the next slide we see the itinerant magnetic moment on iron. We can tell that its spin density wave is suppressed by nickel substitution, but 3D magnetic order survives at the lowest temperature up to the least x equals 0.20. What is the most important? That the iron nuclei experienced the transferred hyperfine magnetic field due to the europium 2+ ordering for nickel substitution samples with x upper than 0.04. And the next slide, the last one, it's the europium 151 europium spectra for 3 to sample for at the 40 kelvins, 300 kelvins and 4.2 kelvins. And what it's interesting for us, it's this spectra when we observe magnetic order of europium regardless of nickel content, and we can distinguish the title tilt angle between the magnetic moment and main axis of electric field gradient. And here it's 90 degree, here 2, and here we have 0. Here we have 31 degrees. So the europium localized moments order and change orientation with nickel content. The change of 4F spins order from antiferromagnetic to ferromagnetic take place simultaneously with the disappearance of spin density wave 3D order, and it's the evidence of a strong coupling between magnetism of europium 2+ ion and conduction electron of iron, nickel, arsenic 2 layers. And here is a simulation how this can look like. So we see the suppressed of spin density wave and change of orientation of magnetic moment. Thank you very much for your attention.
You studied in your investigation very complex solid-state system. What is the leading idea? Why it's necessary to have so complex sample? What you like to find in the end? Yeah.
I want to even investigate coupling between magnetism of europium and with iron. We're looking for here something like nematic phase, magnetic nematic phase in this sample, in this type of superconductors and separate compounds.
Deep fundamental science. Is deep fundamental science.
Yeah, this is the old problem of the coexistence and competition between magnetic ordering and superconductivity, and this is very non-trivial problem. Then I have a question.
I have a short question. In the beginning, you have shown a resistive anomaly below the critical temperature Tc. In the early beginning. Yeah. Yes, on the right, on the bottom. Yes. Haven't you observed similar anomaly in other iron-based superconductors?
It's observed with superconductor with europium. It's connected with europium magnetic moments because europium order in this temperature here.
Okay, so, in europium-based only samples.
Yeah, I didn't see it. It's in different samples.
Thank you.
I also have a short question. You showed the beautiful data on the europium spin rotating with substitution and so on. Does it happen in step-like fashion, like spin-flop transition or continuously?
It's rather continuous.
Continuously.
Yeah, because we have different content of. Okay, maybe it's not shown here because I have only it's not superconductor, but for example with different content of nickel, but it's not that we observe that it's simultaneously change. It's not flop.
Okay. Thank you very much.